This lecture builds on the previous ones on central limit theorem and standard error. So we'll start to see now how those building blocks were so important and so amazing in statistical inference. And this is going to be setting up a lot of what we're going to be doing up through the end of this section on quantitative analysis. So this lecture will define confidence intervals and their related cousin, margins of error, and talk through an example to see how we can use confidence intervals. So let's think about how all of this relates to larger ideas of probability. The central limit theorem enables us to make inferences about population parameters from our sample. And this is even if the data is not distributed normally in our population. So we can treat it as if it's normal when we draw a sample. Imagine that you want to know what the mean of a population is, but you don't have all the information about the population. You can only take a sample. The sample mean will be a pretty good estimator of this population mean. But our population might differ from the sample just due to chance. As I defined earlier, this is what we call sampling error, right? So it's just due to some sort of fluke. And this means that our sample statistics, say the mean of our sample, may not be exactly the same as the underlying population parameter, the population mean. But it's probably pretty close, right? Okay, so let's use our example once again of the average height of American women. And so we see that the mean height in our sample is that women are 65 inches. The actual population mean is 64 inches, not identical, but it's a pretty good estimation. And the question is, how good is this estimation? That's what the confidence interval does. It establishes the likely range for our population parameter. Okay, so it establishes whether we can assume that 65 inches is basically the same as our population range. So let's define this a little bit more and move into some very basic formulas. The confidence interval is a probability of a likely value of a population parameter that you're able to draw using your sample. So thinking about this for the mean, the confidence interval would be looking at what the average height of American women is. And say your 95% confidence interval based on the sample that you've drawn is that you say we're 95% sure that the actual population mean would be somewhere around 65 inches, plus or minus 1.2 inches, okay? So this means that there's a 95% chance that the real population mean, that mean height of women, is between 63.8 inches tall and 66.2. Now it's possible that the real value is outside of that 95% confidence interval of 63.8 to 66.2. It's possible it's actually 63. This could happen if we had a really unrepresentative sample, but that's pretty unlikely. We can say that with 95% confidence that it's somewhere within that band. And margin of error is a term that you might see a lot with polling. So this is the confidence interval that we get for a proportion. So you might say, well, what percentage of American electorate supports greater intervention in Syria? And the result, 95% confidence level, is that you can say it's 40% with a margin of error plus or minus 2%. Meaning that if we were to look at our larger population, we would say that we're 95% sure that the real level of support among Americans is between 38% and 42%, right? It's roughly in that range. So I'm going to go through how we calculate a confidence interval for a sample mean. And the idea here is to hopefully give you a little bit of the intuition without going into much hairy math along the way. So step one, this is up to you. You decide what your level of confidence is. Do you want 95% confidence, 99% confidence? Typically in political science, we use 95%. 99% would make you extra certain, but 95% usually works okay. So then we calculate the sample mean, see previous lectures about how to do that. Calculate the standard deviation of our sample. Again, see previous lecture on how you calculate standard deviation. I'm just going to skip over that step to keep us focused on the confidence interval. and we calculate the standard error. So you should see the last lecture. I'll put the formula up here just to remind you. This is the standard deviation of our sample over the square root of the sample size. All right. And then let's say the next step would be calculating the confidence interval. So let's say we picked 95% level of confidence. That would be the X bar here, which means the sample mean, right? So that would be the sample mean that we observe plus or minus 2 times the standard error, right? And so this will give us the 95% level of confidence. At a 99% level of confidence, same formula roughly, except it's 3 times the standard error. So let's go through an example. So we are polling 100 Colby alumni and asking how much did they donate to the college in 2015. All right, so this is our poll. We see here our N is 100. Okay, so the mean donation size is $700, and we get the standard deviation of 600, and then the N, as I mentioned above, is 100. So we are able to estimate what the mean donation would be for all Colby alumni based on this result. To do this, we calculate the confidence interval at the 95% level. That's the level we've chosen. So here, X bar, this is the mean donation size, 700. Okay, that's already given. And to calculate the standard error, we take the standard deviation. So in the numerator, we have 600. And then we divide that by what's in the denominator, which is a square root of the sample size. Square root of 100 is 10. So 600 over 10 is 60. So with 95% certainty, we can say that the mean donation of all Colby alumni lies between 700, right, that's X bar, plus or minus 2 times the standard error, or 60. So that means that we're able to say that it is between $580 and $820. So using an example of margin of error, imagine that we are polling 100 prospective voters in South Carolina Democratic primary, and we find that Hillary Clinton's at 55%, Bernie Sanders at 45%, and there's a margin of error here of 7%. So can we say with a lot of confidence that Clinton really is ahead of Sanders? So here, to do this, we calculate what Clinton's support is. And so we say that Clinton has support of 0.55, so we're expressing 55% here as a proportion. So plus or minus the margin of error, and that is 0.07. So we would say that her support is between 48% and 62% of voters, right? So that's where we're at. For Sanders, do the same procedure. 45% is a proportion of 0.45, plus or minus our margin of error of 0.07. So that means that Sanders' real level of support is between 38% and 52% of voters. The key here is that the intervals are overlapping. This means that we're not actually sure if Clinton's really ahead, right? So look at this, the 48% lower bar for Clinton, and then there's a 52% upper bound for Sanders. And so that means that there's a possibility that they are even, that it's neck and neck. And so we're not able to say with a lot of confidence that Sanders really is losing to Clinton. It's a dead heat here. So, suppose you got that polling result and you want to tighten your confidence interval. To tighten your confidence interval, you have to reduce your standard of error. And so there are ways to think about doing this. So here again is the equation for the standard of error. So let's just think logically. If you wanted to reduce your standard of error, you have to do something to get this equation of the standard deviation or the square root of the sample size smaller. So 2 ways you could do that. Hypothetically, you can reduce the size of the numerator, meaning you can decrease the standard deviation. So the challenge is that that is not under control of the researcher. So you can't actually do that, but it's just a way that hypothetically one standard error could be reduced. So the next one is to increase the size of the denominator, increasing your sample size. Now this is under the control of the researcher. So this would be what you'd want to do if you're trying to tighten your confidence interval. Let's add a caveat here that this sounds nice, but it can get really expensive really quickly. So, you might double, triple your sample size, but since you're taking the square root of it, the amount that your confidence interval gets tighter is not going to be dramatically tighter. So as it gets larger and larger, you have to make a judgment call about what is your good enough standard error. What level of uncertainty are you willing to expect? And so typically when we're doing polls, we don't get a standard error that's much below 2% because it's getting astronomically expensive.